For the final long question on this classwork, we're given 20 equally likely events in the sample space. If I was to write out all 20 events, I'd write the brace, E1, E2, E3, E4, E5, all the way up to E20. Basically what that means is, since they're all equally likely, they each have probability of occurring of 1 divided by 20, or 0.05. When we then define sets A, B, C, and D, based on how many of simple events are in each of these, we can see what the probability of the event occurring is. A is defined as having these 10 events. If each of the events occurs with probability 0.05, 10 times 0.05 tells me P of A is 0.5. The other way I could see it is there's 10 events divided by 20 possibilities. That would also get me to 0.5. Event B has 4 events. 4 out of 20 would get me to 0.2. Event C has 10 events. 10 out of 20 gets me to 0.5. And event D has 6 events. 6 out of 20 gets me to 0.3. So we're given this information, and from that information, we're asked to find all of these. So the first thing we're asked to find is A complement. If I wanted to write out everything that belongs in A complement, I'd look at A and say, what's missing that would be in the sample space? So E1's there, I don't include it, but it's missing E2, E3, E4, E5, E6, E7, E8, E9, E10, and E20. If I count up how many things it's missing, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and put that over 20, that would give me the correct answer. But for complement problems, there's an easier way to get there. The complement is everything besides A. So if we already know that P of A is 0.5, probability of A complement is just 1 minus P of A, or 1 minus 0.5, which gets me to 0.5. You can do it either way, but if they ask you to list the events, you have to do it like this. If all they ask you is for the probability of A complement, it's usually easier to just do 1 minus A. Same idea for D complement. Here's what's in D. What's missing is E1, E2, E4, E5, E7, E8, E10, E11, E13, E14, E16, E17, E19, and E20. So here I have listed 14 events that are not in D. I could get the probability of D complement as 14 divided by 20, or 0.7. Or I could just say, well, if probability of D is 0.3, 1 minus 0.3 gives me 0.7. For an intersection problem like 17, it only counts if the event occurs in both places. So here's A and here's C that we're comparing. I see that E12 is in both places, E14 is in both places, E16 is in both places, and E18 is in both places. So these 4 elements are the only ones that I see that overlap both lists. For that reason, I'm going to write in A intersects C, E12, E14, E16, E18. 1, 2, 3, 4 events that fit out of the total 20 events. That's how I get 0.2 for the probability of A intersects C. When I go to do B intersect D, these are the 2 sets that I'm comparing. They both have E6, but I don't see anything else that they share. So B intersect D is just E6, which means the probability of it occurring is 1 out of 20, or 0.05. For A union B, I need to include everything in A, everything in B, and just not write the overlaps. So I'm going to start at the start. I see E1. It's in both sets, but I'm only listing it once. The next lowest number I see is E6, which is in set B. The next lowest number I see is E11. It's in both sets, but I'm only going to write it once. Then I see E12, E13, E14, E15, E16, which I see twice, but I only write once, E17, E18, E19. I'm then going to count up how many things were here. 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, 11. Really, it was everything in A, and then the only thing that we added from B that wasn't in A was this E6. So here we have 11 of the 20 elements. That's how we get 0.55 as a probability. Again, the difference between these two types of questions: intersection only includes things in both sets. Union includes one, the other, or both. Just don't double count things that are in both. For C, union D, lowest thing I see is E2. Then I see E3, E4, E6 is in both, I count it once. E8, E9, E10, E12 is in both, but I only count it once. E14, E15, E16, E18 is in both, but I only count it once. And finally, E20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 things out of the 20 total. That's how I get 0.65. When we get down to the question of A intersects C complement, it's a little complicated. Basically, I look at what's in A intersects C, and I say everything besides that. The good news is we previously did A intersects C. It had E12, 14, 16, and 18. So its complement would have everything else, meaning it would have E1, E2, E3, E4, E5, E6, E7, E8, E9, E10, E11, skip E12, E13, skip E14, E15, skip E16, E17, skip E18, E19, and E20. So I could go ahead and count how many are in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and get this as 16 out of 20. Or I could forget having to do all this hard work and just say, well, I know what a complement is. It's 1 minus whatever the previous probability was. So if this probability A intersects C was 0.2, we can just do 1 minus 0.2 to get 0.8. We would have gotten the same thing if we counted these up and found that there were 16 things that fit. 16 divided by 20 would have also given me this 0.8. When we now do C union D complement, it's pointing back to this list. So basically we want to include everything that's not there. E1 isn't there, E5, E7, E11, E13, E17, and E19. 1, 2, 3, 4, 5, 6, 7. If I do this as 7 out of 20, that would give me 0.35, which is the correct answer. The easier way to get it, well, I see C union D is 0.65. The complement is 1 minus that, so 1 minus 0.65 gives me 0.35. For all these ones above, it was really how many things fit divided by 20. For all these ones below, we're no longer going to be dividing by 20. Basically, any of these conditional statements tell me I'm no longer looking out of the full sample space. I'm only looking as if the sample space is what's after the given line. What that means is, for question 23, B given A, this is only going to be out of the elements in A, so when I go to find the probability, it's going to be out of 10, not 20. Of those 10, what I'm asking is how many appear in both lists. So E1 does, that's one of them that appears in both. E11 does, that's 2 of them. And E16, that's 3 of them. So if we know A already occurred, it was one of these 10 things, 3 of them would count as B also occurring. That's why the probability of B given A is 0.3 or 3 out of 10. When I list what's in the set of B given A, I basically just list the overlap. E1, E11, and E16. But it's on me to know that because of the conditional, it's not 3 out of 20, it's 3 out of how many things are in A. For question 24, D given C, here C has 10 events in it, so we know that it's out of 10. When we look and see where's the overlap, we have E6 that overlaps. We have E12 that overlaps. And we have E18 that overlaps. So that's 3 of the 10, meaning that also gives us 0.3. For number 25, A given D, here, since D comes after the given line, there's 1, 2, 3, 4, 5, 6 things in D. This probability will be out of 6. Of the 6 things in D, the ones that also occur in A are E12, E15, and E18. E12, E15, and E18. That means of the things occurring in D, 6 total things, 3 of them are also in A, so I have a 0.5 probability of getting something that's in A if I know I already got something that's in D. For A given B, it's out of these 4. We have the same thing as B given A as far as what fits in the set, E1, E11, and E16. The difference between this question and question 23 is because it's conditioned on B, this one's going to be out of 4, not out of 10. So my probability is going to be 3 out of 4, or 0.75. For C given D, it's out of these 6 things. Of those 6 things, the ones that are also in C are exactly the same list as D given C. So the overlap is E6, E12, and E18. This time, instead of being out of 10, it's out of 6. So 3 out of 6 gives me 0.5. When I go to do D given A, it's conditioned on A that's out of 10. But I can go back and look at A given D to say, well, here's the 3 things that fit. E12, E15, and E18. That's why it would be 3 out of 10, or 0.3. The final one's kind of a trick. It says, what's the probability that you get something from set C, given that you already know you got something from set C? If you condition something on itself, the probability is going to be 1, or it's going to be 100% chance. If we know we already got something from C, what's the chance we got something from C every time? So if I really had to write this out, I'd include everything in C as what counts. E2, E4, E6, E8, E10, E12, E14, E16, E18, and E20. So there were only 10 possibilities in C. All 10 of them are also in C because it's itself. That's why it occurs with probability 1, where it happens 100% of the time.